waves and pattern formation in Physarum. And let's see, that's not on. Wait a second. And I will do an introduction in Physarum, which you heard already in Hans-Günther Dobereiner's talk on Wednesday in some detail, so probably I can be quick there. And in the introduction, I will also make a link to other works on active fluids and mechanochemical patterns, because there's some interesting cross-connection. And in the main part, I will start first with a simple model, and this should be the pointer, on mechanical-chemical waves in an active poroelastic medium, and then I will go to a more realistic, more detailed model based on some of the experimental things known about Physarum polycephalum, but following very similar general ideas. So this you saw probably already. So Physarum is often studied in that large-scale form. So it's a multi-nuclear organism which can grow very big. It lives in woodlands, it feeds on organic material, and it's basically a bag of protoplasm with many actomyosin fibers, and that's because it was studied. That's also a reason why it was studied for a long time, because it's very nice to get actin from that. And more recently, people looked in more detail on these large-scale dynamic networks for transport. So they are dynamically changing, and they can optimize. Physarum can optimize. Well, I shouldn't say Physarum can. The growth of this network is optimized for depending where food is and how the external conditions are. You can look at this as with topological means, and I guess Hans-Günther Dobereiner spoke in some detail about that. What was interesting to us was actually another thing. You can do something else rather than looking at this very complicated network of veins, and actually these veins are dynamically changing and pulsating, and some oscillations are going on. You can just take one of these large veins and suck a little droplet out, and then you have what is called a microdroplet, which is now much smaller. So it's typically 1 to a few millimeters in diameter. And these droplets are stable for quite some time, let's say a couple of hours. And you can look at them, and one nice thing is they show nice deformations in the height profile. And that has been studied by a couple of groups. And I learned that actually when I was visiting Hokkaido University some years ago. And I was quite fascinated by the pattern. So what the colors here show is really deformation patterns. And there is something they call standing waves, which you could also call counter-rotating multi-arm spirals. There is like something which you may call defect or spiral chaos in a more descriptive way. And then finally you get also typically in the long rate, after a longer time, you get antiphase patterns. That means the center of the cell is just down when the boundary is up, and it oscillates really in antiphase. And you see also spiral waves and traveling waves. So actually you see many things which you know from reaction diffusion system, but I remind you what is really measured is deformation waves. And that's why I got interested in that system, because at the time, or still now, we look also at the modeling of cardiac dynamics, which is often described as a reaction diffusion pattern of the electric excitation of the heart. But at some point, when you talk to doctors, they always say, well, but you should get contraction into that, and some groups have really started that. But of course, modeling contraction in a three-dimensional, let's say, mammal or human heart is a very complicated problem. The geometry is complicated. Heart fibers are very anisotropic and have very complex anatomy. And so that sounded much simpler and maybe solvable on the lifetime scale of a PhD student. So we assume that this is basically probably isotropic material. It's relatively small, and since the droplet is clearly much longer than high, we even will reduce it to two-dimensional dynamics. So this is the experiment, and here you can also see the deformation amplitude. So the numbers, so this is an initial state, and the numbers just refer to different types of patterns. And the deformation oscillation, when you just look in one point in this organism, go from 1 to 10%. So it's also rather mild deformation, which makes the model a bit easier. Now, the idea that we had was that we look at this as a two-phase model for these droplets, really. So if you look at in a cartoon of these droplets, you could say there's typically some rather big pores, and there's a relatively dense cytoskeletal network, and of course there's fluid inside the droplet. And when you were talking to the experimentalists, what they thought was driving actually these deformation waves, they said it's very well known that there is an intrinsic calcium oscillation, And probably that's is really what is driving that. So and calcium actually acts different, say, than in cardiac cells in Physarum. It relaxes the tension, actually. So when you have a lot of calcium, the fibers relax, while if you have just a low calcium concentration, they contract more. And so the idea we had then was we just look at this as a spongy medium with pore size on scales of micrometer roughly, and we model as a two-phase system with a solid cytoskeleton and a fluid cytosol. And for that, we could adopt a two-phase model for cellular dynamics written up by Dembo and Alt. Of course, the calcium actually introduces some, I mean, there's first of all molecular motors throughout the system, and we assume that these active stress produced by the molecular motors is then regulated by calcium as an inhibitor. And all of that together we call active poroelastic description. Now, I said there's some interesting links to more general topic of pattern formation in active systems. So we say this is an active poroelastic, but it has some similarities to what is called active fluids. Active fluids is, of course, a wider topic. I think in various articles you find definitions. This is a complex fluid where energy is injected by active internal units. In the case of cells, typically people think of molecular motors, and we're all aware of a lot of work on active gels, active fluids, and so on. And of course, another way is suspensions of self-propelled bacteria, and that's actually the field I was working on for a couple of years. I will not talk about that today, but for a long time, we were considering gliding bacteria or as self-propelled particles, and Fernando Perani is here, so he can tell you more about that. And more recently, due to Sebastian Heinreich, who's a postdoc now in my group, and who started some collaboration when he was in Oxford with Johan Dunkel and Ray Goldstein here in Cambridge. Swimming bacteria is also a very nice pattern-forming system, it turns out, but it has some fundamental differences to these gliding bacteria. And probably Ray advertised it already Monday morning, but since it's the last talk, I mentioned that here. Johan Dunkel will speak about that this afternoon. But the Physarum topic is, of course, the other type of active fluid, if you want. It's about cells, cytoskeleton, molecular motors, and cytosolic flows. That's actually the point which makes it a bit more complicated than modeling cardiac tissue. Cardiac tissue is bigger, has more complex anatomy, but there's, of course, no flows, while it turned out in the process that the cytosolic flows play an important role if you want to understand these experimental patterns seen in these Physarum droplets. And one theme that links it to our general discussion of modelers and experimentalists in cell biology is that these active fluids, of course, can be maybe seen as an extension or an alternative to the standard reaction diffusion mechanism proposed back by Turing and also tried out in many models. All right, this transparency probably I don't have to say too much about. The pictures you've seen in the previous and many other talks. So standard assumption, cytoskeleton is a network of filaments, and if you look at the response to perturbations, it's solid-like at short times and fluid-like at large times. And the poroelastic description actually refers more to this regime. So we look at this as a solid-like. But while models which look at active fluids or maybe active gels, they probably address more the large time behavior, as we also heard in other talks before. And then we assume it's a viscoelastic solid then, and it is active due to motors or the regulation of motors by calcium in the case of Physarum. All right, and in a nice small review article, Joe Howard, Stefan Krill, and Justin Boss from the MPE for Cell Biology in Dresden actually stressed that these mechanochemical mechanisms may provide a nice alternative, and it's actually seen in many cells and tissues already. So the idea is you have, on the one hand, these active cytoskeleton, active fluid properties like viscosity, and then this determines the mechanics, but the mechanics then induces some flow inside the cell, which can lead to gradients of chemical agent or biochemical agents or motors, which then feed back again on the mechanics. So this cycle is an interesting thing to look at. And one nice paper where this was illustrated in a very simple way is also this Swiss Rev letter by Frank Jülicher and Stefan Krill's groups. And so they said, well, let's look at large times when we can look at the cytoskeleton as basically like a viscous fluid, but then of course there is activity in the cytoskeleton just by the fact that there's motors, and they may initially be homogeneously distributed, but then a local increase of motor concentration leads then of course to active transport in the fluid, because that leads to stresses and gradients, and it can be a positive feedback, as I showed for a very simple model. So in the end you may get really a large density and homogeneity for these molecular motors, which then is counteracted by flow. So there is a cycle in there, and that's nicely demonstrated in that paper. Now here, the motors actually are activating the tension, and that's going to be different in our model. But maybe some more words on this poroelastic idea. In Physarum, you have some microscopic pictures where you see that, but there are some other recent studies of more standard cell types where you also see that eukaryotic cells can actually behave poroelastic, and typically on very short time scales. And one experiment was done by putting tracer particles of different size into a cell, injecting it locally, and then looking what's happening after a long time. And if these beads were very small, then they were distributed homogeneously. If they were intermediate, they stayed still in near the place where they initially put, and if they were even bigger, they were almost localized in a particular part of the cell. And one conclusion was that just means that the cell itself, at least on the scale of these experiments, cannot be really a fluid, because otherwise it would maybe not matter so much what happens. So, and there's more detailed studies recently published this year, which again makes that argument that the cytoplasm can be a poroelastic material on short time scales. Nice thing about Physarum polycephalum, of course, also elastic behavior has been studied, and it seems that has much longer relaxation times. This fluidization takes longer, and therefore it's a good candidate for that poroelastic behavior. All right. Now just a simple model, not yet looking at Physarum. I already said some things. The cytoskeleton is a solid phase, the cytosol is a fluid phase, and of course they are coupled in the sense that we think of something like a sponge. We start with a homogeneous motor concentration, and actually the motor concentration isn't really a variable. So we neglect really transport of motors in the cytosol, but we assume this homogeneous concentration. And then we assume that there is a regulator which affects the activity of the motors. And with this regulator, we were thinking of calcium, as we shall see later in the example for the detailed model of the Physarum. But here we just assume there is a regulator. Of course, you could also add an activator, but then it turns out nothing interesting happens. So there is no feedback which leads to pattern and destabilizes things. So it's really the sign of the feedback given by the inhibitor which plays a big role here. Then we wanted to model the cytoskeleton as a viscoelastic solid, so we just used the Kelvin-Voigt model. Of course, there's many other works which use that, but here we use it in the context of this two-phase description. Of course, other authors have used the Maxwell model, and it's also interesting to look at that. But here we said we are under short time scales where we think cell is well described as a poroelastic medium. Now let me get into some more detail. First, we followed basically in the spirit of the simple paper on active fluids by the Dresden group. We derived analogously an active poroelastic model, and one of the interesting features is, rather than having just stationary patterns as for the active fluids, it creates mechanochemical waves, and this was just published some months ago. Oops. All right, and so basically we have a fraction of fluid and fraction of solid in the two-phase model, and they add up to 1 and are constant. We have the deformation field of the solid described by a variable u. Now we're still in one dimension. And one important assumption, we always assume that deformations are small. Otherwise, the equation actually becomes much more complicated. But we assume that the deformations are small, and we use only linear elasticity here, okay? Then there's the velocity of the fluid that describes the fluid phase. And we have the concentration of that regulator C, which then is transported around by the fluid through the pores in the poroelastic medium, but it affects the elasticity of the solid phase by interacting with the motors in the cytoskeleton. We also assume incompressibility. That's just necessary because we need to close the equation. And then we say the stress is a sum of two contributions. I already mentioned the Kelvin-Voigt model. So this is the stress in the solid phase, and there is an active part, T. So T is the active tension, while we treat the fluid phase simply as a viscous fluid. Okay, and then we assume the force balance in both phases, and then after some. Okay, and then we look also at the whole system in the body reference velocity system. And after some manipulation, we then get these three simple equations. This is simply, or maybe this is simply transforming the incompressibility relation to have a relation between these body reference, the velocity in the body reference frame of the fluid and the deformation field. This is just a diffusion attraction equation for this regulator. So there is no production or degradation of that regulator. So it's really overall in the system, there is a conserved quantity of that regulator. So there is something like a hidden variable, which is the average concentration, C0. I don't discuss it in any more detail. And from the two force balances, we simply get this relation again between W, U, and here the active tension comes in, and the beta, which comes from some kind of track force. So here's the viscoelasticity, and the active tension, I said already, that has to be inhibited. So increasing C would decrease the active tension. Obviously, you could also argue the other way around, but then you can simply change the sign of that prefactor, and then one sees that then it's not really a feedback which produces interesting patterns. We can, by using Darcy's law, we can actually identify this parameter, which is a nice thing. I mean, it's not simply a factor which describes the track force, but it's given by the viscosity of the fluid in the pores divided by the permeability, which is proportional to the radius of the pore. So we can at least make an estimate of the dimension of this beta, and then altogether there's a coupling now between the deformation of the solid and the fluid velocity, and the regulator comes also into play. Maybe before I should go on, I didn't write down boundary condition, but we assume that the boundary is fixed. So if we think in one dimension, we think of a line of finite length, and at the boundary there is no deformation, so U is 0 at the boundary, and there's also no velocity. So W or V is also 0 at the boundary. And for the regulator, we assume simply Neumann boundary conditions. I mean, you have to specify that to complete the problem. We can then introduce dimensionless variables. So the Peckley number, which is this mechanochemical coupling constant, which determines how strong the effect on the active tension is if the concentration of this regulator changes, divided by the diffusion constant times the factor beta. And then we have also a ratio from the diffusive to the elastic timescales, which is given by M, and that gives a very nice phase diagram. I mean, of course, there is this parameter of the overall concentration, which is hidden. So if there would be no regulator, of course, you would get no instability, and the diagram isn't changed, but the position of the lines is maybe changed then. All right, and so the simple state is 0 here, so we have linear stability here. So if we have no mechanochemical coupling, the whole system is stable. I mean, it cannot do much. There's no reaction going on. There cannot be something like a Turing type instability, so it cannot do anything. But then if you increase the mechanical coupling, depending on how the other factor M is, you get instability when the leading branch of the eigenvalues looks like that. So it's a long wavelength instability, but it's oscillatory. So you could say that's something like an oscillatory phase separation. If you go further up, some of the modes become real, and in the special case of M equals 0, so when this elastic modulus goes to 0, which is practically probably not a very relevant thing, you go again to static patterns only. Then it looks very much actually like the model for the active fluids, but it's a different kind of model. Okay, now we can do simulations. So this is linear stability. Here we plot the space-time plot of this one-dimensional system with respect to the concentrations. Now, if you go above that line where you get linear instability of the basic state, which is actually a state where there is no deformation and no flow, and also homogeneous concentration of the regulator, all the three fields start to develop waves here. In this case, after some initial transient where we put a bit of noise on this reference state, the instability develops very nicely, standing waves. Now, if you change the parameter m, there's a region where you go to some kind of more irregular behavior, and finally you get these traveling domains, and due to our boundary conditions, these domains are always reflected at a boundary. And that's actually something you see also experimentally in Physarum, as I will show later on. All right. So this is a phase diagram. You can do the simulations, and they fit relatively well with the prediction of the linear stability analysis. I think here, this one I have to press. You can also write a two-dimensional equation, because of course you can't reproduce much in terms of the Physarum, and that's a finite element simulation of the two-dimensional version of the model I described. And after a while, you see there's some internal oscillations coming up. Again, the concentration is shown. And first you see some wave which goes just back and forth in the cell, but after a while there is a bit of a symmetry breaking, and you see a rotating wave. So that comes already close to some of the patterns in the Physarum. So you see the calcium concentration has a rotating wave. You will see also the deformation wave if you would have plotted that. And so you see really a wave-like thing, which is actually a very simple model. So before I go to the more detailed model, let me just summarize what we've done so far. So we showed that you can have mechanochemical wave if you assume you have an active poroelastic medium where the active tension is actually regulated by an inhibitor which can be transported around by flows in the cells, and that's necessary as a feedback to get that instability. It's an oscillatory long wave instability, and the length scale that is for this mechanochemical wave is actually given by the ratio, but the square root of the ratio of some kind of effective viscosity and this drag coefficient, which depends again on the viscosity of the fluid and the porosity of the medium. And that's a nice alternative to Turing mechanism, because in Turing mechanism, of course, as we all know, you need some kind of diffusion, but you also need some reaction, and the typical scales are then given by the square root of the diffusion divided by a reaction rate constant. Now, these mechanochemical things can produce pattern on itself, but it's also interesting actually and that's a theme I will follow a bit in the second part when I get more detailed about Physarum, is a coupling to reaction diffusion. And one nice thing about the active fluid paper of Stefan Krell and Frank Jülicher actually was that they also coupled to a standard reaction diffusion system their mechanochemical active fluid, and showed very nicely that actually the range where you see Turing patterns becomes much bigger. Because I think last year we had in Newton Institute a meeting celebrating Turing's famous paper from '52, and we heard the history, how people try to do that in chemistry. And one big problem was always a Turing pattern works only if you have very different diffusion constant, and that's sometimes very difficult to realize, even if you are free to play with the chemistry. But coupling to activity may release that strong restriction, which actually led to like a 40-year delay between postulating the simple idea by Turing and the first really nice chemical experiments on that. And then, of course, in the next part, I want to go to the Physarum patterns. And there were two conflicting ideas. The one was that there is a bit more. So the regulator is not simply passively advected around and moves diffusively. It's also oscillating by an internal mechanism of the cell, and that is mostly promoted by mathematicians in Japan, collaborating with experimentalists. But there's also an idea that you have a pure mechanochemical model, which I found actually very appealing. But reading the literature and discussing with experimentalists, we actually opted for the second thing. So it's a more complicated model. It seems that many experiments actually point towards the fact that there is this calcium oscillator. So in a way, Physarum are actually one example where you couple this poroelastic active medium, which can in itself already produce mechanochemical wave to a reaction diffusion dynamics of a calcium oscillator. Okay, and this is a paper we just submitted. It's longer, but here we really try to incorporate as much as possible from the experimental literature. Just a reminder, these were these nice patterns that I showed you in the beginning we were after. You can also do space-time plots, so you have velocities, you have information about the deformation amplitude and so on, so you have some things to compare with, so it's probably worth trying to do that as realistic as possible. All right, so the realistic model is a bit more extended. Luckily, there was a model already for calcium oscillator, which was based on some complicated biochemical process. So it was simply free calcium concentration coupled to some enzymes which were serving as calcium buffers. So it's not the regular calcium oscillators we know from other cells, which work with the endoplasmatic reticulum, for example, which also studied a lot in biomedicine, I guess. And then we still keep the incompressibility conditions. We use an equation for active tension, which is similar to what I had in the first part. And we also derived the two-dimensional mechanical equations for the poroelastic media, basically using a similar approach than in the one-dimensional simple model I showed you in the first half. So the idea is we have this two-phase mechanical system, and it has an additive feedback with this regulator calcium, but this regulator has in itself some interesting oscillatory dynamics, and that oscillator drives again contraction. So it's a little bit more complicated. So the new part is actually this calcium oscillator, which are basically these two variables. But since we want to couple to the mechanics, we have to give a relation of the active tension to the concentration of free calcium and these buffer concentration. So I don't remember exactly what the enzyme was, what was described by Phi. And you could do an instantaneous coupling, but in experiments you also observe that in Physarum there's always a phase shift between the calcium concentration and the active tension, and we could introduce that phase shift by just assuming some kind of relaxation time, tau t. Here, that's just a two-dimensional version of the model I showed you already on the previous transparency, and there is an active tension element in here, and then the two things simply are coupled, and this is then the full set of equation, which we then will do again linear stability on, and also numerical simulations. So the first three equations are the calcium oscillator, but now there is a deformation, there is a flow field, and that leads to some attractive transport. We neglect any transport in the second variable phi to make things a bit simpler, and then this active tension will be determined by these two chemical variables, and it will couple back into the mechanics just in this way. So it's a very simple coupling of two systems, which I in itself I think very well understood. I should say, well, historically we started actually with a more complicated model, as it often is, so the notation is a bit different. So here what I called fluid in the first part is now called sol, and what I call the solid is now called the gel, but that just a thing. So now what's happening, you can again look at the reference state, which is zero deformation field and zero velocity field, and then if you have no mechanical coupling, you can look at different situations. So that's the situation we look mostly at. So we have some instability already in the zero mode, and that's related to a frequency. So that's the imaginary part versus the perturbation wave number. And so this is simply like the calcium oscillator. That's what you expect, some parabolic shape. So since there's only diffusion in the free calcium, also no sign of a diffusive instability here. But if you increase then the mechanochemical coupling above a threshold value, you actually get a different dispersion curve, so you get a maximum at a finite wave number. And you can, of course, change the parameters of this oscillator to a situation just below the onset of oscillation. And then what's nice is then if you then increase the mechanochemical coupling, which we do starting from zero here to small values, intermediate values, large values, you actually get really the signature of a Turing instability. So since we have this oscillator now, there is no conservation of the calcium concentration over time anymore, and so basically the eigenvalues is no longer here at zero, and it becomes a short wave instability, or in pattern formation notation, a type 1 instability. It's still oscillatory. All right, now simulations. I said simulations, we mostly looked at a case where already the calcium dynamics in itself was oscillating. So the linear stability of the non-moving state was in that sense not so interesting. But you can still look at the dispersion curve and can distinguish two regimes. So here's the mechanical coupling strength, and that's the drag coefficient beta. And here we were not so sure which is the relevant scale for the pore, so we played really with that parameter. But you can actually change it over a quite wide range of parameters, and the type of patterns that emerge and the way and their properties do not change too much. So, but this black line is basically the strength of mechanical coupling that is needed, that the dominating mode is actually a short wavelength mode, so it appears at a finite Q. So that's basically when the dispersion curve has gone from a parabola in its real part to a curve which goes upward and down. And okay, and then you can of course do simulations, and the simulation confirm actually that this change is significant, because if you stay below that curve, you mostly get homogeneous oscillations. So no spatial gradients, no patterns. But if you go above that curve, these non-zero wave number mode grows fastest, and you see different types of waves. You see sometimes coexistent, spiral, and traveling, so then it depends on the initial conditions. You see a region where you mostly see spirals. You see complex regular patterns, irregular patterns, and so on. Another thing you can look at is the Peckley number, which is now which is now given by this combination. So it's very much analogous to what I had in the first part, and also there, if the Peckley number gets large, things get interesting. Okay. That's a good question. That's an invention of our PhD student. I guess I asked the same question, but I mean, it's typically, I should say, it's typically something like a pair of counter-rotating spirals. So you don't see it from one snapshot what it is. Can be also more than two counter-rotating spirals. So it's something where you would see some long-term periodicity, but probably it's also more than one pattern. You just summarized and lumped everything there. Yeah, complex regular is a funny name, I agree, but just a way of summarizing. Another thing I said already, the pore scale defines that better, but this is just to show that the dominant wavelength, so that's basically this maximum of the dispersion curve, which belongs to the wave number at the maximum of the dispersion curve, is not really changing the pattern wavelength. So if ft is small, the length scale is quite big, and in a small system you may not even see anything, but then over a relatively large number of parameters, not much is changing here in this wavelength. And numerical simulations, you can look at different things. Now here he looked actually, the simulations were done, and what you see is the Haidt field, but you could also plot the concentrations, and the arrows give the flow field which is associated with that. Again, the instability starts then with the basic state, but after some time the noise will turn these waves. I will just show you some movies in a moment, and so you can't see much. Our experimental colleagues, which have done these experiments and not yet published them, believe that this is similar to what we see here. Probably here there's some image analysis would do good, but what you have is actually is like the tip of a spiral, if you want, or a rotating patch which goes around in circles. That's very much like the movie I showed you already for the simple model, but we also did some movies which I'll show you in a minute. But maybe first, since we put realistic parameters in, maybe something about quantitative results. So the deformation of the Haidt profile I showed you in the beginning were 1 to 10%, and we get actually similar values in this region just above these two lines I had in the phase diagram, where say just above the onset of spatial instability, if you want, where you see spiral and traveling waves. So that's intermediate mechanochemical coupling. If you go to large mechanochemical coupling, you get actually huge deformations in the simulation. And in a way, if you are really precise, you should say, or I should say that one violates these conditions. I mean, then linear elasticity will not be enough. And actually also the incompressibility condition will not really hold if you get too big deformation. But I will show you some qualitative results on this regime because they look nice nevertheless. The model can be extended because it's also known that these droplets are not really homogeneous. They have a soft boundary layer, and that's probably the explanation for many of the antiphase patterns. Another thing is the wave velocities. In the simulation, they come out as being relatively slow, 1 millimeter per minute. In an experiment, they are at least in a similar range. And the pattern wavelength is also basically on the order of the diameter of the droplet, which is typically 1 to 2 millimeters. So one could probably do more if I had more time, but I will end the talk actually with showing some movies. So this takes a while. So now, again, the deformation field is shown, and these black things are actually the errors of the flow field. And now the instability has built up, so you see a spatially inhomogeneous system that looks actually initially a bit like counter-rotating spirals maybe, or funny type of oscillation. But in the long term, the dynamics settles into, again, a rotating patch, which is what we call a spiral in this context. Now, very often this coexists with what's called traveling waves, and which is also experimentally observed. So that looks also like a complicated transient, some translation, some rotation motion, but in this case, actually, the pattern is then really, in the end, again, a wave which goes up and down. And so it's basically a wave which goes from right to left and then gets reflected, and so you get some traveling structures in there. I said, if you have very large couplings, then the model is just qualitative, but there you get also other symmetries of patterns. So here you get something which I would call, well, it's some sort of antiphase oscillation. So the rim region and the central region are typically oscillating out of phase, and that generates a lot of fluid flow. And finally, you see also when you go to very large mechanochemical coupling strengths, the dominating perturbations which grow fastest have smaller wave numbers, and then you see also more than one object, and you see many little fragments. And well, questions, of course, you could longer, and maybe that would settle, but here look, at least on the scale of simulation, that there's some kind of quite irregular dynamics going on. Oh, it's still the same. So the boundary is basically fixed. So there's no deformation of the boundary, and there's no, the velocity is set to 0 at the boundary, and there's a 0 flux boundary condition at the outer for this chemical, for the calcium concentration.
These arrows jump somehow big of the boundary.
Yeah, that's probably more, I don't know which.
In the previous.
Yeah, I don't know if that is an artifact of his visualization. Yeah, sometimes they but it's the same boundary condition.
Can you show the video again? Can you show that?
Okay, sure.
The left one.
Left one, okay. In both. Where the arrows should be maybe scaled a bit smaller, but
the arrows seem to be mostly parallel to the surface when they're large, and they're quite small when
they're small, they seem to. They mostly show either towards or away from the boundary on the left side. But as I said, I mean, this antiphase pattern actually you get closer to the experimental pattern if you allow for a softer boundary region, which I guess the experimentalists tell us is the case. All right, good. With that, I'm almost done. So I showed you that if you just have the active poroelastic system without any reaction or intrinsic dynamic of the chemistry, you get already mechanochemical waves with a long wavelength instability. For Physarum, probably it's the right way to look at it is some coupling between this poroelastic and an oscillatory calcium dynamics, and that leads then to a short wavelength instability and to all the patterns I showed you just in the movies. And you get many different patterns depending on the mechanochemical coupling constant and drag coefficients and other parameters in the system. Of course, the outlook is some of what we do is a bit confined because we use linear elasticity, but of course you can introduce non-elasticity of the deformation, as Len Pisman and Michael Köpf did in a recent paper. I think you didn't include any feedback by flow, but it was rather a different way, the deformation impact on the chemistry, but many of the ideas actually are very similar to that paper here, except that here already non-linear elasticity is used. And finally, and that's probably what we want to do in the future, is if you wait long enough, or if you make these droplets a bit bigger, they start to move. And that's, I think, first of all, an experimental challenge. And I think first experiments are already going on. I don't know if you showed anything on Wednesday, but this is quite an interesting thing. And then, of course, you have to release our fixed boundary. You may also change the elastic model. Poroelastic may not be the right description anymore. And some of the questions that Igor just discussed in the talk previously, how do you introduce that? What's an efficient way to include moving boundaries will also appear here. But for today, that's all I wanted to say. Thank you. And of course, acknowledgement to a number of co-workers. Sergio Alonso did help a lot in the simple model. Markus Ratzowait did most of the work in his PhD thesis. That was a joint project with Harald Engel, and Markus Hauser from Magdeburg did show us some of his unpublished experiments and actually provided a lot of expertise in discussions on the model, and of course to funding agencies and also the institute. Okay, thank you. You can ask questions.
I didn't see where the size of the drop came into the dimensionless parameters in your phase diagram. Because presumably if the drop's too small, nothing happens.
Right. I mean, we did rescale the system. Basically, we scaled to dimensional quantities, and then you get a dimensionless wave number, but you can always translate back. So, for example, for typical cells, the time scale is on the order of 0.1 seconds, 7 micrometer. That's this work that people in Harvard did. For Physarum, it's a bit different, but well, actually, Physarum I use.
I'm right in thinking that if the circle radius is too small, and everything else being given, if the size of the drop is too small, nothing happens. So there is a critical transition in that.
Well, if I would non-dimensionalize the model, of course, if I start with a 1 millimeter droplet, it will have some typical length scale, and that will also be related to my results there. But it's in there, and you're perfectly right. I mean, if the coupling is very weak, you may already get that instability. But if it's 5 millimeter and the drop has only 2 millimeters diameter, we will not see too much of that. That's true.
Where you see in your diagram where you have transition from homogeneous solutions to inhomogeneous.
Which you mean this one?
Yeah.
Yeah, that's basically the line.
It's here.
Somewhere there.
Actually, experiments are it's not so easy to estimate things. Often it's more an order of magnitude, but there is some indication that the mechanical coupling strength may be in this region or so, but yeah. All right.
If you want to relax the boundary,
Right.
would you then need to include adhesion with a substrate, or I mean,
Probably yes. I mean, I think you will run into the same problems that Igor told us about. You may do that in a qualitative way and not look at that, but I think in the end, what the interesting thing is also for experimentalists is to see how the droplet will start to move, or how it may even grow out in these vein-like structures and so on, or how growth front of Physarum is moving, and then you need to include some interaction with the substrate if you want to do it quantitatively. Probably will be over several steps, as we saw nicely in the previous talk.
This is a question. I mean, you said there's like 10%, 5% height variation in the drop.
Yeah.
We don't see that here. I mean,
Okay.
It's a fixed depth, and we see variations within the distance.
So we see, I should say that was a bit tricky because we went, I mean, you could do a full 3D model, which was computationally difficult. So we went to 2D and we said the local deformation in the plane is a measure for the height deformation. So he made some simple estimate.
But did the radius? I didn't see it.
No, but that's also in the experiment. The radius is constant, but you have inside deformation, so it's locally compressed, and these deformations, 1 to 10%, is, let's say, the amplitude of the deformation field if you look at it as waves. Yeah.
But so conceptually, there might be a way of having the edge of the ring deform?
Yeah, sure. And I think that's what I said. I mean, it will happen probably in the long run, and probably even in these experiments you may see a little bit. But the way the original experiments were presented, it sounds like it's almost constant. And we had played with some models where you do that, but they don't change much on the pattern unless something dramatic happens, like the drop would start to move.
Because at the beginning you said there's height deformations in the drop.
Yeah, the height deformation are the local. So basically, there's a deformation wave coupled to the concentration wave of whatever the regulator is, calcium and Physarum, I believe, and also to the flow field. So, and that's what I'm
Yeah, so probably when we see such strong flow towards the edge, you have something like a ring forming, right?
Yeah, something like that.
Final questions? People are hungry. So let's thank all the speakers of the morning.